Hi students, today I am going to explain what is crystal field theory, what are its assumptions and important features, how the d orbital splitting takes place, what is crystal field energy, etc. Let's see. So let's start with the crystal field theory. What is it? So what is the theory about? So the crystal field theory. So it is a model for the bonding interaction between transition metals and ligands. So the interaction between the metals and the ligands are explained in this theory. So it describes the effect of attraction between the positive charge of the metal cation and negative charge of the ligand. Here we can understand there is ions formed. So there is an electrostatic attraction created between the metals and the ligands. So positive charge of the metal cation and the negative charge of the ligand. So when the ligand approaches the central metal ion, there will be a degeneracy of electronic orbital exists. The degeneracy is created in the d and f orbitals, which because of this degeneracy, these orbitals are broken down due to this static electric field produced by surrounding charge distribution. Because of the charge distributed around the metal ion, because of ligands, the d orbitals or f orbitals are broken down because of the electric field. So what are its assumptions? What are the assumptions of crystal field theory? So the first one is the transition metal. So it will act as a cation, the central cation, and the ligands donated their lone pair of electrons to the vacant orbitals of this cation. And we can say that the ligands are point charges. So the ligands are considered as a point charges and the bond is 100% ionic bond. These are held by electrostatic force of attraction. The negatively charged electron cloud of ligands, as already told, metal acts as a cation and positive charge and the ligands as a negatively charged. So when the negatively charged electron cloud of ligands repels the valency electrons of the cations. So the electrons which are present in the cation, that is metal, it will repel it. So the electrons which are negative charge of valency electrons of cations are repelled with the negative charge electrons of ligands. What happens? The degeneracy will be lost. In the d orbitals, degeneracy is lost and they will attain different energies by splitting. So this splitting, I will explain it very elaborately after this. So like this, the d orbitals degeneracy is lost and different energies are formed. So what are its features? What are the important features of crystal field theory? We'll see. So CFT does not consider the bonding to be covalent. I already told in its assumptions, it assumes that the bond is 100% ionic. So it will not consider the bond is covalent. It consider it to be ionic, means the bonding between the metal cation and the ligand arises from electrostatic attraction between the nucleus of the metal cation, which is positive charge, and the partial negative charge present in the ligand, and the interaction between the electrons of cation and ligand is entirely repulsive. So there will be electrostatic attraction between the nucleus of the metal atom and the ligand, and there will be a repulsion between the electrons of cation and the ligand. So because of this interaction, the splitting of central metal d orbitals occurs. So but it does not consider any orbital overlap here, like in VBT theory, valency bond theory. So next, so we will see the crystal field theory elaborately. So I already told it is the It tells about the nature of bonding between central atom and a ligand. But in valency bond theory, I already told the bond between the ligand and central atom is covalent. But according to our theory, CFT theory, ligand and central atom is purely ionic. So let's see, according to CFT theory, the central metal atom and the ligand have ionic interaction. Now you are crystal clear that CFT theory, it is considering only ionic interaction. So in a free transition metal or ion, there are 5d orbitals. We know that there are 5d orbitals present. So which are designated as, we already know, dxy, dyz, dxz, dx square minus y square, dz square. So when splitting of d orbital takes place, these will be divided into two sets. How? Because of their nature of the orientation in space, how they orient in space, depending on it, they are divided into two sets. What are the two sets? Let's see. First, when we take dz square and dx square minus y square, so these will be having lobes lying along the axis. So the lobes will be along the axis. So dx square, dy square. So as they are, the orbitals are present along the axis, they are called axial orbitals, and these are called EZ orbitals. E means doubly degenerate sets. So as they are doubly degenerate sets, they are called EZ orbitals. So dx square, y square, dz square. So these two are called EZ orbitals. And the other three, when we see dxy, dyz, dzx lobes lie in between the axis. So these two lie along the axis, whereas these three lie in between the axis. So these lobes are present in between the axis. They are called non-axial orbitals, and these are also called T2Z orbitals. T2Z orbitals because they are triply degenerate sets. Because they are triply degenerate sets. Let's see. So when we see the axis x, y, z, and these are present in between the these axis, as the lobes are present in between the yz, so dyz, and between the x and z, x and z, xz, and between the x and y, dxy. So as these are present in between the axis, they are non-axial orbits, and they are also T2Z orbitals. So like this, the splitting of this d orbitals is more important for the degeneracy to created. So when a metal ligand is attacked by the ligands, so the approach is more important. When a ligand approaches on its axis, as I already told, like in x square minus y square and dz square, when they approach along the axis, so it experiences more repulsion. It experiences more repulsion, so it is more energetic. Remember this, because it experiences more repulsion, it is more energetic. So, and when a ligand approaches in between the axis, then it experiences less repulsion. So these three are having less repulsion, so less energetic, and these two are more energetic, and these three are less energetic. Then how the splitting takes place, let's see. So this is the energy and the 5d orbitals when we give some average energy. So orbital in spherical crystal field, after that it splits. So I already told dx square minus y square and dz square have more energy, so it will be upper energy, more energetic, so up. And dxy, yz, zx. These three are having less repulsions, so less energetic. Like this, these are splitted, and when no splitting takes place like this, so under the influence of approaching ligand, these 5d orbitals which were originally degenerate split into two levels. So T2g, this is lower energy, and Eg, higher energy. The separation of 5d orbital metal ions into two sets having different energies. These two are having different energies, high energy, low energy, is called crystal field splitting or energy field splitting. And when we see here delta 0 or 10 dq, so its energy is from lower energy to higher energy. Delta 0, it is also called crystal field energy. So here it is 10 dq. So when there is no splitting, when we consider as 0, then 0 to less energetic. So here it is minus 0.4 delta 0. Whereas from no splitting, or when we take it to the higher energy, more energetic, then easy, then it will be plus 0.6 delta 0. So together it is 10 dq. So in the middle, when there is no splitting, it is 0 plus 0.6 minus 0.4 delta 0. So next, so I will explain it. So when the 5d orbitals are splitted, up is easy, I already told, and down is T2g. The extent to which these two sets of orbitals are split is denoted by delta 0. How much it is splitting is denoted by delta 0, that is equal to 10 dq. As the barycenter, this is where no splitting occurs, is called barycenter, must be conserved on going from spherical field to an octahedral field. So when it is going from a spherical field, from here to an octahedral field, from spherical field to octahedral field, this barycenter should be conserved. It should be conserved so that the T2g sets should be stabilized and Eg set should be destabilized. So the energy for T2g is equal to 2 by 5 of delta 0, that is equal to 10 dq. So 2 by 5 of delta 0, or we can also say that 2 by 5 is equal to 0.4 delta 0, or simply 4 dq. This is 4 dq, this is 6 dq, 4 plus 6, 10 dq. Remember this. So like this we splitted. So 2 by 5 delta 0, or we can say 0.4 delta 0, or 4 dq. 4 dq, 6 dq, 10 dq. So, and so less than that of degenerate orbitals. When we compare with this, this is 0.4 delta 0 or 4 dq is less, and energy of EZ orbitals, if we take, that is 3 by 5 delta 0 or 6 delta 0 or 6 dq. So higher than the degenerate d orbitals. When we compare the barycenter, it is that much high. Just remember, this is plus 0.6 delta 0, this is minus 0.4 delta 0, and this is 6 dq, this is 4 dq, together 10 dq. This is 2 by 5 plus 3 by 5, we will get 5 by 5, 1. So delta 0, thus this is 1 delta 0 plus 3 by 5 minus 2 by 5. So like this we can consider. Then this is all about octahedral complexes, how the crystal field splitting occurs. So up to now I explained in octahedral complexes how the splitting occurs. Now we will see crystal field splitting, how it takes place in tetrahedral complexes. So in tetrahedral complexes, how the crystal field splitting takes place. So we can say that reverse happens in tetrahedral complexes. That means there will be a reverse splitting. So in octahedral complexes we saw the 5d orbitals, it will be raised to average energy and the splitting takes place. So here T2Z, so lower will be T2Z and higher will be EZ. Yes, no. So means dxy, yz, zx will be lower, dx square minus y square, dz square will be up. So reverse of this is here lower will be dz square, dx square minus y square, and higher will be dxy, yz, zx. And this will be 6 dq and this will be 4 dq, total 10 dq, and this is the Baresch center. Same like before, but reverse splitting takes place. So what is the reason for this reverse splitting when we see? Because of its geometry. Octahedral complex have different geometry, tetrahedral complex have different geometry. So the reason for this is mainly because of its geometry. The d orbitals interacts less strongly with ligands in a tetrahedral arrangement. When we see a tetrahedral arrangement, the d orbitals interaction will be little less interaction will be there compared to octahedral complexes, and we can see only 4 negative charged regions, whereas in octahedral we can see 6. So because of this, what happens? The electrostatic interaction will be 1/3. So if we consider like this, when we consider all the factors like this, we can give one equation. So tetrahedral splitting energy is equal to 4/9 of tetrahedral octafield energy. So delta T means crystal field energy of tetrahedral complexes. Delta O means crystal field energy of octahedral complexes. So tetrahedral complex energy is 4/9 times of octahedral energy, means it is less. So because of why the tetrahedral energy is less than octahedral energy? Because of weaker d orbital ligands interaction. I already told, because of its geometry there will be a decrease in the electrostatic interaction. So because of this, interaction is weakened and decreased electrostatic interaction, and d orbital ligand interaction is weaker. So like this, the energy will also be decreased. Like this we can explain the crystal field splitting in both octahedral and tetrahedral complexes. Then the next is, what are stronger ligands, weaker field ligands? Let's see. So the ligands which cause a high degree of splitting of d orbitals. So whatever are the ligands which make the splitting of d orbitals to more, it will split to more, they are called higher field ligands or stronger field ligands. We can see it will cause a high degree of splitting, more splitting, that is called stronger field ligands. And when it splits a very small degree of splitting, only very less splitting, then it is called weaker field ligands. Very easy, ligands which cause high degree of splitting, it is called stronger ligands. Which causes a low degree of or very small splitting, they are called weaker field ligands. We can see higher field ligands, lower field ligands. Then depending on this, a electrospectrochemical series is done. So how the ligands, whether they are strong ligands or weaker ligands, so they are arranged in a magnitude of how the splitting takes place. So when ligands are arranged in order of magnitude of crystal field splitting, the arrangement thus called as spectrochemical series. When we see this, so iodine, bromine, SCN, scandium, chlorine, S2NO3, FOH, like this we can see a series. But is it easy to remember like this? So to make it easy, so one trick is there. Before that I will say these are strong field ligands, these are first ones are weak field ligands because they are in increasing order. So weak field ligands, At the end is strong field ligands. How can we find whether it is a strong field or weak field ligands? Let's see the trick. C donors, carbon donors are all strong field ligands, and N donors, nitrogen donors are strong ligands, and O donors, oxygen donors are strong field ligands, and halogens are weak donors. Means halogens are weak field ligands compared to oxygen donors, compared to nitrogen donors, compared to C donors. So this is a very simple trick we can remember. When we see C donors, it is a strong field. N donors, they are also strong field but less than C donors, and compared to O donors, and last halogens, they are very weak field ligands. Like this we can remember easily. Then spectrochemical series is over. Then how the splitting takes place in octahedral field according to the weak ligands, and when the weak ligand is taken and strong ligand is taken. I already told in a weak ligands the splitting is very less. So in octahedral field T2G will be down, lower energy, EZ will be high. Yes, no. So the 5d orbitals will be splitted very less in a weak ligand. So T2Z and EZ will takes place, and how the pairing of electrons or filling of electrons takes place. It takes place according to Hund's rule and Pauli's exclusion principle. Though you know this, just I will revise it to make it easy. So what is Hund's rule? So according to Hund's rule, electrons in degenerate orbitals will not pair until almost all must have singly occupied. Until all first singly occupied, pairing will not take place. Pairing will take when all are filled with single electrons. And Pauli's exclusion principle, electrons prefer to move in orbital of lower energy. First lower energy orbitals will be filled, after that higher energy orbitals will be filled. These two principles we should follow while filling the electrons. Let's see when in the case of weak ligands. So first 1, 2, 3, 4, 5. So like, because the splitting is very less, easily it will fill first 5 electrons, and pairing starts from here. So according to the Hund's rule and Pauli's exclusion, first lower energy is filled, after that higher energy, Pauli's exclusion principle. All are singly occupied first according to Hund's rule, after that pairing started. Here again, so 5, 6, 7, 8, 9, 10. So like this the pairing starts. So in a weak ligand. What happens in the case of strong ligand, we'll see. The splitting of d orbitals will be more. So how the pairing takes place according to Hund's rule and Pauli's exclusion principle, if we see, so the first it will occupy the lower energy according to Pauli's, and but the energy gap is so much, what happens, it cannot fill the 4, 5 here. So instead of that, pairing starts here only. So 4, 5, 6. After that it will go to higher energy. So 7, 8 it is filled. After that pairing again starts here, 9, 10. So like this the strong ligands will be filled. In the weak ligands normally 1, 2, 3, 4, 5, again 6, 7, 8, 9, 10. Like this it is filled. But here pairing starts here only, and after that here it will be filled. So like this the pairing starts in weak ligand and strong ligands. So pairing, for pairing energy is required, that is nothing but pairing energy. So it is the energy required to pair electrons against electron-electron repulsion in the same orbitals. So in the case of weak ligands, so delta 0 will be less than the pairing energy, and in case of strong ligands delta energy will be greater than P. So what are the factors affecting this delta 0 crystal field energy? So maybe the nature of the metal ion, charge on it, and also the quantum number like 3D, 4D, 5D, whatever it is. And the complex geometry is important. Octahedral different way, we know. Tetrahedral square planar, there will be geometry different depending on the delta zero changes, and the nature of the ligand, whether it is a strong ligand, a weak ligand, what is that, that also depends. And the position of the metal ion in the transition series, electrotransition series, how the metal ion, so spectrochemical series we saw in that also, how the and also in the transition series how the metal ion is there, what is its position, depending on that. So the delta zero will depend. So these are the factors of delta zero. So up to now we saw this, and we will see next in this what are low spin and high spin complexes. So the complexes in which there is an arrangement with minimum number of unpaired electrons. There will be very less unpaired electrons. They are called low spin or spin pair complexes. Means maximally they will be paired. There will be very less number of unpaired electrons. That's why it is called spin pair complexes or low spin complexes. The complexes in which there is an arrangement with maximum number of electrons, they are called high spin or spin free complexes. So let's understand this. When we take high field ligands, means that is strong ligands, where there is a large splitting of d orbitals, it is very unfavorable to put electrons in high d orbitals. So because it will be filled in the lower energy, to put the electrons into high energy, so much of energy is needed, so and it is unfavorable for that. So low d orbitals are first completely filled before filling the upper sets. It is already, I explained this, yes, no? So here the pairing already here done. After that the pairing started here. So that are called low spin, because what is low spin? No unpaired electrons or less unpaired electrons, already it is all paired, yes, no? So that is called low spin complexes. In the case of low field ligands, reverse happens. Where there is very small splitting of d orbitals, so it is very easy to put the electrons in the upper also, higher energy set of orbitals also, then to put in some low energy orbitals. That's why first both will be filled, after that pairing starts. So that is why these are called high spin orbitals, because there will be maximum number of unpaired electrons we can see. So these are high field ligands and low field ligands. Just again I will see, when there is a large splitting in high field ligands, when there is a large splitting of d orbitals, it is very unfavorable to put electrons to high d orbitals. So low d orbitals are completely filled before filling of upper sets. So they are called low spin. Whereas in low field ligands, the splitting is very less. It is easier to put electrons into higher energy set of orbitals. So low energy orbitals, and it have high spin. So we will see the crystal field splitting energy values of octahedral and tetrahedral complexes. So when we see the CFC values for various D systems in a octahedral, we know that how many electrons will be there in a D. So 10 we know. So in a high spin complexes, as we know, T2Z means XYYZ XZ, lower energy. So as we consider lower energy, and high energy is Z square x square minus y square, that is easy. So when we take high spin complexes, means there is weak ligand. In the case of weak ligand, high spin complexes takes place. So how the filling takes place. So when one electron is there, so it will be filled here. So the energy is 4 dq. So because it is filling the lower energy here. So in the case of weak ligands and high spin, so let's see, it is high spin. When there is only one electron, here it will be filled, and the energy is 4 dq. So when it fills 2 electrons, so 1 2, then it will be 8 dq. 4 plus 4, 8 dq. When 3, 1, 2, 3, 12 dq. So when it contains 4, then what happens? Here 1, 2, 3, 4. So here what happens? It is 0. As we know, it is 0.4 or 4 dq. Yes, no, it is 6 dq. So when 1 electron 4, 2 electrons 8, 3 electrons 12. So when it comes to 4th electron, here it is. When we take 6 dq. So it is 6 dq. And when all are singly occupied, then it will be 0. Okay. Then when we come to 6th electron. So 6th electron where it is. So 1, 2, 3, 4, 5 fully occupied. 6th is coming while pairing it. So 6th is pairing it. So when we see 6th electron, it is pairing in the first. So 4 dq. When 7th, second one is pairing. So 4 plus 4, 8 dq. When 8th electron is coming, it is pairing the third electron down, T2Z. So 12 dq. So 8th electron, 12 dq. When it is pairing here, first 6th electron, then it is 4 dq. 7th electron, it is 8 dq. When the 8th electron is filling, it is 12 dq. Yes, no? Then 9th electron, where it will go? Just we know, here it is up. 9th electron it is filling. So again it is 6 dq. Again when 10th electron is filling, we know that when it is all are paired, it will be 0. So 0. So just remember, when the first electron 4 dq, second 8 dq energy. So 3, 12 dq. So when here it is pairing 6 dq, we will not consider this because it is in the upper state. Higher energy is 6 dq. When all are paired singly, 0. When all are paired also, 0 here also. So when first is paired 4 dq, second is paired 8 dq, third is paired 12 dq. When here it is pairing 6 dq. When all are paired, 0 dq. This is about high spin complexes in the weak ligands. When we take the low spin complexes, it will be different because it is a strong ligand. So what happens? First will be paired here. So first, so it is 4 dq only. So first one here it is occupying. So 4 dq. Second one here it is occupying. Again 4 plus 4, 8 dq. Right. So when third one is pairing. 12 dq. So same like in weak ligand. When it comes to fourth ligand, because there is a splitting is more. Because the splitting is more, it cannot go here. So pairing starts here only, as already I told. So in the case of fourth one, so pairing started here only. Then how will get 16 dq? Because we will get 16 dq. How? So 12 plus, again here it is started 4. So 12 plus 4, 16. So how? Here it is 12 dq. Up to this it is 12 dq. And pairing again started here. So plus 4, 6 dq. 16 dq. Again pairing started here only again. So fifth will be pairing started. Again 16 plus 4, 20. 20 plus 4, 24 for next. Yes, no, 6 electrons. So now it is completely paired. Yes, no. So here it is completely paired. Then it will go to the next higher energy. Here the filling started. Then how will take here? Pairing already over. It is 24. So 24. Again when it comes to here, it is, I already told, in the upper energy it is 6 dq. So here also when barrier center is there, it is 6 dq. So remove 6 dq energy from this 24. So 24 minus 6 is 18. So 18 dq. So again here the 7th electron filled here. 1, 2, 3, 4, 5, 6, 7, 8. So when 8 electron is entered here, again 18 dq minus 6 dq is 12 dq. Again it is filled here again. So 12 minus 6, 6 dq. 6 again here it is filled, completely filled. It is 0. 6 minus 6 is 0. So like this we can see in low spin complexes. I already explained how the filling takes place. Very easy. As the splitting is more, 1, 2, 3 it is filled, because it cannot go to up. Here only it will start filling. 4, 5, 6. After that it will go there. 7, 8 will be filled. After that 9, 10 will be paired. Like this. Like this the pairing takes place in the octahedral complexes. Then what is the CFC values for tetrahedral field? I already told you in tetrahedral field there will be a reverse splitting takes place. So how the reverse splitting takes place? dxy yz xz will be up, dz square x square minus y square will be down. So let's see how the splitting occurs here. So let's see first. So lower is dx square minus y square, dz square I told, and higher is this 3. So we will see first one electron enters dx square minus y square when one electron is there. When 2 are there, again dx square minus y square, dz square. When 3 are there, again the filling starts with dx square minus y square, dz square, dxy. Again 4, again it will fill 1, 1 here. And when it is 5, so completely filled. So up to 5, and pairing starts, d6 pairing starts here, d6 pairing started here, d7, d8 pairing started here, d9, d10. So how about the energy we'll see. So here it is minus 6 dq. So up is 6 dq. So it is reverse, no? So minus 6 dq, double minus 12 dq, and here so minus 8 dq. So because minus 12 plus 4, because it is plus 4, so this is minus 6. So minus 6 minus 6 minus 12, and this is minus 6 minus 6, and it is next so low higher energy it is, so plus 4. So minus 6 minus 6 minus 12 plus 4 minus 8 dq. Then again minus 6 plus 4 plus 4. So we can calculate minus 12 plus 8. That is nothing but minus 4. So again here we can see all the fields are singly occupied 0. Again when we see here it is minus 6 dq, because pairing started here, so minus 6. Again here 2 are paired, so minus 6 minus 12. Again 3 pairing started, so minus 6 plus 4. Again minus 8 dq. Again here, so minus 6 plus 4 minus 4 dq. Again 0. So like this the splitting takes place in the tetrahedral complexes also. So we got an idea how to fill the electrons in both. Then so this is about crystal field theory. So it has also many. So this is about crystal field theory, and it has many merits and demerits. So we can say that what are its merits means it is very simple and apply for theoretical basis for quantitative correlations, even for empirical and semi-empirical numbers also. And we can predict the magnetic moments with temperature as well as the magnetic properties of some complexes. It also predicts the spectrochemical properties. It explains some spectral problems also, and it treats certain kinetic and thermodynamic properties. See, so these are the merits. When we see the demerits, so it always gives importance to metal d orbitals, and it will not consider the ligand orbitals. So it will not consider the ligand orbitals. It ignores the ligand orbitals. It only places emphasis on metal d orbitals. So all the properties depends upon ligand orbitals will be outside the scope. So we are not considering the ligand orbitals, and it did not explain the charge transfer bands and intensities of absorption bands and transitions, and even it did not consider the pi bonding rather in common occurrence. When we see a complexes, we may see back bonding, pi bonding, etc. So it did not explain that. So because of poor Lewis base ligands here. So it is not a satisfactory for the relative strength of ligands. No explanation why H2O water in a spectrochemical series has strong ligands than OH and halides. When we compare with the OH and halides, why H2O appears as a strong ligands. So these are the demerits of a crystal field theory. Thank you.